Okay, back at it with number 9. Here we have this reaction. It's combustion reaction, and it's the hydrogen balloon combustion that we do all the time. And so they want us to figure out when it stops being a spontaneous reaction. So let's look at this reaction a little bit before we start. So we already know it's a combustion, and that tells me it's going to have a negative delta H value. And then if I'm looking at the phases on the molecules, we have 3 moles of gas in our reactants, forming 2 moles of gas in our products. So that means we have a decrease in entropy. And if we look at the data that they've given us, we have the individual values for each molecule's entropy and enthalpy. And we're going to figure out what these values that we've predicted up here are by doing products minus reactants with the data in the table. And then once we have those values, we can use our favorite go-to thermodynamics equation to address the actual question in the problem. Okay, and so we can start by figuring out what our delta H of reaction is going to be. By doing our products times their coefficients, we'll have 2 times the value for water minus our reactants times their coefficients. We'll have 2 times the value for hydrogen gas and just 1 times the value for oxygen gas. Okay, and so we can plug in the values from the table here, and we'll have 2 times the value for water, which is negative 241.8 kilojoules per mole, minus 2 times 0 plus 0. Okay, and the reason that the values are 0 for hydrogen and oxygen is just because they're in their standard states, their standard elemental forms. And so they have a delta H and a delta G of formation of 0. And so when we solve this, we get a negative 483.6 kilojoules per mole for our delta H of reaction. And this number that we've calculated matches with our expectation of having a negative delta H. Okay, so we can say that our delta H of reaction is equal to negative 483.6 kilojoules per mole. And now we're going to do the same kind of thing to figure out the enthalpy, or the entropy change in our reaction, except we're going to plug in the standard entropies for each of the molecules. So here I have the same type of setup for products minus reactants that I did for the enthalpy, but instead I have it for entropy here. And when you solve this out, you get a negative, like we expected, 89.6 joules per mole Kelvin. So I'm going to make note of this number up above also, but when I do that, I'm going to convert it to kilojoules because we need our units of energy to match in all of our terms. So this will become negative 0.0896 kilojoules per mole Kelvin. Okay, so we have our delta H and delta S values for our reaction, which is the first step to solving this problem. So the question at the core of this problem is, at what temperature does the reaction change from being spontaneous to non-spontaneous? So we know that when delta G is negative, we have a spontaneous reaction. And when delta G is positive, we have a non-spontaneous reaction. So the point where that switches is going to be 0. between there. So what we can do is say, let's pretend delta G is 0 and solve for the temperature where that happens, and that will tell us where our cutoff point is between spontaneous and non-spontaneous. So up here, if we were to plug in 0 for delta G equal to delta H minus T delta S, we can go ahead and subtract over T delta S, which is, or the minus T delta S, so we're going to add that over. Where that T delta S is equal to delta H. And we can say that our temperature is going to be equal to delta H divided by delta S. Okay, and so then we can just go ahead and say the temperature where we're going to have this turnover is going to be negative 483.6 kilojoules per mole divided by negative 0.0896 kilojoules per mole Kelvin. And when we plug that in, our temperature will pop out in Kelvin, and it ends up being 5,397 Kelvin. So pretty hot to make this non-spontaneous. And so at that temperature now, our unfavorable entropy term is being magnified and magnified until it's canceling out the favorable enthalpy term. Okay, so our first step was to figure out our delta H and delta S for the reaction overall. And then we could use those overall terms to plug into our thermodynamics equation, keeping in mind that it switches from being spontaneous to non-spontaneous when delta G is 0. And then from there it's just some fun algebra. So for number 10, we're trying to figure out when delta S for the reaction is positive. And we have all of these reactions. And what we're going to do is we're going to compare the phases in the reactants to the phases in the products. And to do that, we're going to remember that the gas phase has the highest entropy, where the solid phase has the lowest entropy. We can just see if it goes from being a less entropic phase to a more entropic phase. So we've actually already seen this first reaction, but here we're going from 3 moles of gas down to 2 moles of gas. So we have fewer moles of gas, so this will have a negative delta S. So that one's out. In B, we're going from a gas to a solid, so that's definitely a negative delta S. In C, we're going from aqueous to solid, so that's also going to be a negative delta S. In D, we're going from solid to some gases. So we're taking something with a very low entropy value and making 2 things with very high entropy values. So that one's going to have a positive delta S. But let's look at the last one too. So we have 3 moles of gas going down to 2 moles of gas. So this one does have a negative delta S. Confirming that D is going to be our correct answer here. Okay, for number 11, they want us to get the standard entropy change for the following reaction given the table. Okay, and our reaction is just taking a diamond, reacting it with oxygen to make carbon monoxide, which seems like quite a waste. But here, we're going with some solid, some gas, and making more gas. So I'd predict that this has a positive delta S value. we can go ahead and use our table to get the number for that. And this looks like a scary table, right? But it's not. It's fine. It's just a table, and it has a lot more info on it than we need. And so the column that we're going to use is going to be this column, because it gives us the individual entropy values. And we can use those to do products minus reactants. And we just want to make sure we pull the values for the right compounds. So we know we need diamond. So that's the value for diamond. We know we need oxygen gas. That's here. And then we need carbon monoxide, which is this value. Okay, and all the other values we don't care about. Okay, so then we're just going to do our products minus reactants. So we can say that the delta S of our reaction is going to be equal to our 2 moles of carbon monoxide minus our 2 moles of diamond and our 1 mole of oxygen gas. Okay, and then we just plug in our values. We'll have 2 times 197.67 joules per mole Kelvin minus 2 times our diamond value plus our oxygen value. It's kind of cool having this table and seeing how the gases have really a lot higher standard entropy values than the solid. Okay, so we have our setup, and then we just plug it in to see what the number ends up being. And I get that it is a positive 185.4 joules per mole Kelvin. And that positive matches the prediction that we made based on the phases in the reaction. So the answer here is just B. Okay, in 12, we are picking which reaction has Kp equal to Kc. And so both of these values are KEQ, equilibrium constants. When we put P or C, we're just saying, hey, heads up, I used pressure to calculate this value, or hey, I used molarity to calculate this value. Because it'll make a difference which type of value we plug in terms of the number we get out. So we have this equation, and it gives us a way to convert between units. It's just a fancy unit conversion. And so what it's saying is we want Kp and Kc to be equal. So for that to be true, I need this term to be 1. And sure, maybe there's some crazy combination of temperature and delta N that magically makes this number equal 1. But what we usually think about is this being equal to 1 if delta N is equal to 0. It doesn't matter what the inside of that parenthesis is. If you put it to the power of 0, it'll just become 1. Okay, so we want to look for where delta N is equal to 0, and delta N is just going to be the moles of gas from the products minus the moles of gas in the reactants. Okay, so in A, we have 0 moles of gas on the left, and it goes to 1 mole of gas on the right. So here our delta N is going to be positive 1. We're gaining a mole of gas. In B, we're going to have 2 moles of gas becoming a total of 4 moles of gas. So our delta N here is going to be plus 2. And in C, we have 2 moles of gas and we make 1 mole of gas. So our delta N is going to be negative 1. In D, we have 3 moles of gas on the left and only 2 moles of gas on the right. So our delta N is going to be negative 1. And then in E, we have a total of 3 moles of gas on the left and 3 moles of gas on the right. So our delta N here is going to be equal to 0. And that would mean Kp will be equal to Kc. So in number 13, we have this reaction, and they want us to figure out Kp for it if they give us some initial values and an equilibrium value. So for equilibrium problems, it's always a good idea to start by just writing what your equilibrium expression would be. So here we'll have products, their coefficients, divided by reactants to their coefficients. And I just want to remind you not to include any solids or liquids in your Kp expressions. We say that their value is 1. Okay, so we have our Kp expression, and what we eventually want to do is plug in equilibrium pressures instead of just writing in the molecules. So here they give us initial values and equilibrium values. We can see how they change. So we're going to use an ice table. And they tell us we're starting with 4 atm of our N2O2, 3 atm of NO, and 5 atm of NO3. And then the only other number they give us is to say that at the end of this we have 2 atm and 2O2. Okay, so when we do our ice tables, we use the stoichiometry of the reaction to figure out the change. And so we can see that our N2O2 concentration is going down. So we can say minus, and we must be making some of the other things. And then for our change, then we'll just do, say, minus 2x for N2O2, plus 1x for that, and plus 1x for the NO3. And we can combine those into our equilibrium row. So we'll have 4 minus 2x, 3 plus x, and 5 plus x. Okay, so we know that for the N2O2, we ended up with 2 atmospheres partial pressure at equilibrium. So we can go ahead and say our equilibrium term for that is equal to 2. So our x, if we go ahead and solve that, it's just going to be 1. And so if we know our x, we can use it to figure out how the NO changed and the NO3 changed. So we can plug in our x here and here to get that their equilibrium pressures would be 4 atm, and 6 atm. And then these are the values that we'll plug into our Kp expression. We can go ahead and say Kp is equal to 4 atm times 6 atm, all divided by 2 atm squared. And this value ends up being 6. And that's it. That's our answer for the question. That's our Kp value. And we know it's already a Kp because we have it in atmospheres and partial pressure. Okay, so the answer here is just A. So now someone went to run an experiment with that same reaction at a different temperature. And at that temperature, our Kp is 25. So let's go ahead and write Kp is equal to 25, and then that is going to be equal to our expression, where we have NO times NO3 divided by N2O2 squared. Okay, so now they're saying we're starting with just 5 atm of N2O2. They want us to figure out what the partial pressure is going to be of NO. Okay, so they're asking us to give us some initial values. It changes and we get some equilibrium value. So we're going to need an ice table. And we can put in our initial values. So we have our 5 atm here, and then we'll have zeros for the other side. And I don't have any of this stuff to begin, so I must be making some of it, so that'll be positive, and we'll use some of that up to do it. Okay. So my change again will be the coefficient times x. We'll have minus 2x there, plus x, and plus x. To get my equilibrium row then, I'll have 5 minus 2x for the N2O2. And then for both of these products, I'll just have x as my value. Okay, and so now what we're going to do is we're going to take the values from our equilibrium row and plug them in to our Kp expression. So I'll have Kp, which they tell us is 25, equal to x times x divided by 5 minus 2x squared. And so you guys can probably see that we can take our numerator and reconfigure it to be x squared. So now we have something squared on the top and something squared on the bottom. And so we can go ahead and take the square root of both sides of our equation. And that'll make the algebra a lot nicer. We can say then we have 5 equal to x divided by 5 minus 2x. Okay, and then we can multiply over, and we'll have 25 minus 10x is equal to x. We can move our 10x over and say 25 is equal to 11x. And so that tells me that x is equal to 2.27. And so now that I know my x, I can figure out the equilibrium pressures of everything. And it asks us about NO, so let's look at that. Its value is equilibrium concentration is just going to be x which we know is just 2.27. So that'll be B. Okay, so these past two problems have been different ways you can use an ice table, and both ways are great. Just helps us organize what's going on, and we can use it to either figure out what our KP is going to be, or use a KP to figure out what our equilibrium pressures are going to be. In problem 15, we have some reaction, and they tell us what the Kc is, 0.4. And so I just automatically write my equilibrium expression, which is going to be B divided by A cubed. And they tell us, let's say we're starting with 3 molar A and 2 molar B. What's going on? So what we're going to do is go ahead and just solve for Q. And Q tells us where we are in relation to equilibrium. So we can figure out which direction we need to move. And so here we can calculate Q by just plugging those numbers into the same expression that we would use for K. So we'll have 2 molar divided by 3 molar cubed, which is 2/27, also known as 0.074. So we can see that our Q is less than our KEQ. And that means our denominator is too big. We have too many reactants. And if we have too many reactants, we must have to proceed in the forward direction to make some products. And so whenever we proceed in the forward direction, that's going to be spontaneous. And that means we'll have a negative delta G. Okay, and so that corresponds to answer choice B. Here in number 16, we have KEQ values for two reactions, and we want to combine them somehow to figure out the KEQ for a new third reaction made up of stuff in the other two. So the way that I always approach these problems is to look at the two reactions and figure out what's present in those that I don't have in the reaction that I care about. So I've underlined those here. The water and the hydroxide don't appear in my third reaction. And so I want to do something to the other two equations so that they cancel. And so right now they wouldn't cancel as written. They would just combine together. And so that tells me I'm going to have to flip one of the reactions. And so I'm going to flip the second reaction because that will make everything cancel out. And it will also get the protons on the reactant side like I want, while keeping the ammonia on the reactant side also. Okay, and so when I flip a reaction, oops, it's important to remember to flip it, but okay, when I flip a reaction, now what was products are reactants, and what were reactants are now products. And so I have to flip my KEQ expression over. And to do that, what I'm really going to do is just do 1 over my KEQ. And that's going to be my new KEQ. And you can see if we kind of pretend like this was never here, if we compare the first equation now with if we combine the first and our new equation, we can see that our hydroxides would cancel and the waters would cancel. And so we would indeed just have NH3 from above plus the protons, making the NH4 plus. Okay, so now I want to combine the KEQ for that equation and the KEQ for this equation to get our new KEQ. And the way we combine K's is to multiply them together. So I'll have 1.78 times 10 to the minus 5 multiplied by my adjusted K. So 1 over 1 times 10 to the negative 14. And the value for that is 1.78 times 10 to the 9th. It corresponds to answer choice E. Okay, and if we had to do any changing of coefficients to make everything cancel out properly, then whatever multiplier we apply to our equation, we'll just put that in the exponent of our KEQ. So if I had quadrupled the coefficients, multiplied everything by 4, then I would just take that KEQ value to the power of 4 to account for that change.